It's about time. It looks like most of you done this, but in case you haven't, go ahead and chat me your first and last name. That'll be used as our role, and we'll go ahead and get started. Does anybody have any questions before we do get started?
Yes.
Yes, go for it, Isaiah.
Uh, is Lab 4 due today, or is that due on next
Yeah, I
week?
gave you a whole 2 weeks on that one because
Okay.
I didn't get it to you in a reasonable amount of time, so I wanted to make sure y'all had plenty of time.
Okay. Perfect. Thank you so much.
No problem. You did see it in the announcement, right?
Yeah. Yeah. I
Okay.
saw that. So I was kind of confused a little bit as to the due date because it typically pops up on the to dos, but
Right.
it's all good. Thank you.
And if anybody's still having any problems with the analyzing motion, downloading the software, or finding other software to use, I'm cool with helping you guys by giving you extensions or whatever, at least on that lab. So just let me know. I did tell a student today, for instance, they were asking if I had any ideas of specific software that they could use in lieu of the software, the Logger Pro software. And what I told them was the software that I actually used is called Video Physics, and Phyphox is another one. Phyphox. That's another one. And then the other one I used was SCI space journal, Journal. So again, that's Video Physics. That's one app that I used on my phone. Phyphox, Phyphox was another one I've used. That one can be used for a lot of different things. I'm not sure Firefox is the best choice for the Logger Pro, but I think you'll enjoy having it. And then Side Journal, SCI space Journal, was one that did allow me to use the video feature to analyze the video and get a plot of distance versus time, velocity versus time, that sort of thing. So if any of you guys still need software other than the Logger Pro, you can do that. Of course, you can also download the Logger Pro from my YouTube, I mean, from my actual Canvas course, as opposed to just the website that was listed in the addendum. Anybody have any other questions? All right. Well, I guess we'll go ahead and get started.
Yeah. I
We,
had one
yeah,
more.
go ahead.
Sorry. For exams, next exam should be on the syllabus, right?
Yes, you have an online test that's supposed to be due this coming Sunday according to the syllabus, and I've already moved that back to the 17th instead of the 15th. And I've also moved chapter 3 and chapter 4 homework due dates back a bit. Chapter 5, you'll see, has some weird date, but we haven't even covered chapter 5, so it's not expected to have an appropriate date, even on the My Lab and Mastering side. So, right now, the only things that are in play are chapters 1 through 4, and I just reset the due dates on chapters 3 and 4, and I just reset the due date on the online test 2. I should also mention I had one student that missed online test one, which was due last Sunday at 11:59 p.m. If you're one of those people that missed it, you're going to get a zero and you're subject to be dropped from the course. But if you go ahead and email me and let me know, I will reopen it and take off points and give you some more time to complete that. And then in the future, you need to make sure you don't miss any more of those. So make sure you guys let me know if you did miss that online test one. So far we've had online test one, and we're getting ready to take online test two. Online test two is already available, but it's not due until the 17th. Anyone else have any questions? All right, well, we're going to go ahead and get started. We're going into chapter four, and chapter four is called Dynamics, Newton's Laws of Motion. And if you look at that, what you'll notice is it opens with a chapter opening question. As always, you guys should definitely do that. The contents for chapter four are 4-1, force, 4-2, Newton's law of motion, 4-3, Newton's first law of motion, I should say, for 4-2. It's Newton's first law of motion. 4-3 is on mass. 4-4 is Newton's second law of motion. 4-5 is Newton's third law of motion. 4-6 is weight, the force of gravity, and the normal force. And 4-7 is solving problems with Newton's laws, free body diagrams. And 4-8 is problem solving and general approach. So those are the topics we're going to be discussing. Your author does tell you that he generally uses reddish slash magenta arrows to represent forces in his free body diagrams, and then he uses, I think he said, green arrows for velocity. Sometimes there's some need for you to put an acceleration or show an acceleration or show a velocity near a free body diagram. That's helpful, but you don't want it to attach to any of the vectors that are on the free body diagram because those things should never be added together. Not only are they adding apples and oranges because they literally have this different units, but they're fundamentally different quantities, so they shouldn't be used that way at all. Now, with that being said, I just want to go into talking about Newton's laws of motion. You really need to spend the time reading this chapter four, at least all of chapter four, pretty thoroughly, because that gives you the fundamentals behind Newton's first law, Newton's second law, Newton's third law. And I want to remind you all that you're also supposed to commit a certain amount of stuff to memory. I told you guys before that when you're taking a physics course or a chemistry course or an engineering course, if you discover that like a whole section of a chapter or even especially a whole chapter, it has a certain name like, ideal gas law or something like that, then as a bare minimum, whenever that section or subs or whenever that chapter or chapter subsection is listed, then you should immediately find out whatever that quote unquote law is and commit it to memory because every instructor sometimes will try to give you a little bit of a freebie by offering you a question like, please state Newton's first law of motion, or please state Newton's first law and Newton's third law of motion, or something like that. And those are supposed to be really chucker questions. But if you're not in on the joke or the implication, then you're not going to get it, and you'll get a bad grade. So I want to remind you, at this point, we've really only started covering Newton's laws, but by the end of the semester, I suspect you should be able to have memorized Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, and not only those three laws, but which one's the first, which one's the second, which one's the third, Newton's law of gravity, as well as what is Newton's law of gravity compared to the Newton's three laws of motion, Kepler's first law of planetary motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion, conservation of energy, conservation of momentum, conservation of angular momentum. All of those are principles that we use repeatedly, and therefore you should commit them to memory. So that's a list. It's on the video. You can look back at it. I'm not going to write down or take the time to write those down for you, but I'll say by the end of the semester, all of those are a bare minimum of what you should know. So let's go ahead and jump into Newton's laws of motion. And I'm going to start off with talking about section 4.1, which is a force. And they have this wonderful little picture of a young lady pushing a shopping cart with like 13 watermelons in it. And what's worse is she's pushing a shopping cart on a gravel road. You know how fun that'll be. But she's also pretty teeny. So I'm thinking 13 watermelons is pretty extensive and kind of heavy, so she's probably not having an easy time of it. But the big point here is what is a force? And if you think in terms of what Galileo discovered, because in fact, if you were to listen to Newton, you'd probably have heard one of the more famous quotes by Newton, and that is, "If I have seen further than others, it's only because I stood on the shoulders of giants." And that sounds really humble of Newton. And if anybody's ever read any of the history of Newton, he is not a humble person. He is brash, arrogant, a little bit timid in the sense that he's sort of shy, doesn't like interacting with people. But he is definitely not humble. And in fact, what's going on there is when he made that statement, he said it in front of the Royal Society, of which the leader of the Royal Society at that time was a guy by the name of Robert Hooke, who was one of Newton's many arch enemies. And Robert Hooke had a little bit of a short man's complex in that he was a short guy. And in fact, what Newton's saying is, hey, if I have seen further than others, it's because I stood on the shoulders of giants, not hobbits like you, Mr. Hook. So you can look at it that way and you say, okay, well, maybe that's the dig. But not only that, he was really paying homage to people like Galileo, for instance. So Newton's first law of motion turns out to be the exact same thing as Galileo's law of inertia, and therefore, Galileo obviously beat Newton to the punch. For some reason, I thought I remembered that Galileo died on the same day that Newton was born. I'm not. I don't know if I just dreamed that or if that's just a memory I had, but y'all might check into that. It's kind of an interesting story because later on, Stephen Hawking is quite proud that he was in fact born on the same day that Newton died. So not the same day by year, but the same date, just many, 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 many years later. So, anyways, that's an ongoing sort of inside joke, if you will. But Galileo, looking at what we had for science at the time, and in the time of Galileo, really the science that was there was Aristotelian science. Of course, we had the Copernican revolution to some extent, but it's still percolating. It's not quite through. And what Copernicus did was suggested that the planets orbited the sun, not everything orbiting the Earth, like Aristotle had suggested. And really, the ancient Greeks had considered that as well, but they knew that if that was the case, they should see something called parallax, which is basically if you're in one part of the Earth's orbit, let's say in June, and you look up at a star, and then you come back and look at that same star in December, you would see that that star that you're looking at would have moved left or right when you went from the June part of the orbit to the December part of the orbit, at least relative to the background stars. They couldn't detect any of that by the ancient Greeks couldn't. So they said either the universe is so big that all those stars are unimaginably far away, or the Earth must be the center of everything. And they just couldn't imagine the universe being that big, so they threw that out, and we ended up with the geocentric model of the solar system, which at that time was the center of the universe, because in that era, and literally up through Galileo and Newton, we weren't sure that there was any more than our star with our planets around it, and then the roughly 10,000 stars that we see throughout the whole year in the night sky. And all of those turn out to be really, really fairly close to us, and all within our own galaxy. We didn't know about other galaxies. We didn't know about other islands of stars. We didn't really figure that out until Hubble looked at what was then called the Andromeda Nebula and discovered that that was, in fact, not a nebula, but another island of stars. And given the science at the time was good, but the data wasn't the best, he estimated that that might be 100,000 light years away, which was way bigger than the universe that they had modeled up to then, but it was way smaller than it actually is. It turns out the Andromeda galaxy is about 2.5 million light years away from us. So that literally means when we look at the Andromeda galaxy, we are looking at it how it looked 2.5 million years ago, because that's how long it's taken the light to get here from there. But still, that is the beginnings of science to some extent. And Aristotle started out with, very basic premises that he considered to be unobjectionable, obvious truths. But we look at them now and say, well, the crap is he talking about? Like, for instance, one of the unassailable logical truths of Aristotle was that the heavens are perfect, and therefore all the shapes in the heavens must, in fact, be perfect spheres or circles, because those are the quote unquote perfect shapes, right? That seems kind of ridiculous to us, but that is the mindset that they had. Not only that, as a result of that, since the heavens are perfect, one of the other things he'd say is that means they're immutable. You can't change the heavens. The heavens don't change, so you can't have anything speeding up or slowing down or reversing and stuff like that. All of those things, of course, are a little contradicted by the evidence, and then over time we build this Aristotelian model of the solar system, which is really the universe at that time. And it basically has the Earth here with the moon orbiting it. And then outside of that is Mercury, orbiting it, and then outside of that is Venus. Outside of that is the Sun orbiting around the Earth as well, and then outside of that is Mars, and then outside of that is Jupiter, and then outside of that is Saturn. That's pretty much all they knew. Uh, that was the model. And basically, it would get off in that they could take that model and they could predict exactly how big those orbits were and stuff like that. But they had to account for weird things like, some stars would always go from right to left, right to left, right to left. And then all of a sudden they'd start changing and go from left to right and get brighter while that's happening. And then they change again and then go right to left to right, left to right, left to right again. So all of that stuff had to be taken into account, and they ended up having crazy models. We'll talk about that a little bit more later. But the main thing is there was clearly some problems, and it didn't hold up. So you could like do a prediction for the next what you think is the next 1,000 years, but within 25 years or so, your predictions were not very good anymore. So they'd have to regroup, look at all the data, readjust all the parameters in their model, and then they could predict the stars again for another 10, 20, 15 years or whatever. And you always had to do that in repetition and repair it. That's why people like Tycho Brahe and Galileo and Kepler, that's how they got their money. Is part of what they did was prepare basically sort of almanacs of where they could find the heavenly bodies in what constellations at what times of year well into the future. Because at that time, astrology, which is a pseudoscience, was actually thought to be a science. And they had to make very specific decisions based on astrological data. So you couldn't, for instance, just if you even look today, we can't schedule, for instance, Easter because it doesn't happen on the same day every year. It actually happens after a series of astronomical events, like you have to have the autumnal equinox or the vernal equinox, and then you have to have a new moon and a full moon, and then so on and so forth. So it literally changes each year. Always under the same conditions, but the main thing is it's not a fixed date. So that was sort of what they had to do with everything. You had to make decisions like, okay, what constellation or what planet is in the constellation of, I don't know, Ophiuchus or something like that. In what constellation is the planet Mars, for instance, because the god of war was Mars, and that would affect their decisions. And how does this king's birth date stack up, and does it look like a good time for that king to be marrying or something? So all of that stuff was part of their government, and they needed good predictions of where those planets would be, and that's what these people like Galileo and Kepler and all those guys did. So now we're coming to Galileo, where basically what Galileo discovered was that no, Copernicus was right. In the sense that the center of the universe was the sun, not the Earth, and that we are just like the third rock out orbiting that sun. And he got in a little trouble for it. There was a inquisition, and there was a trial where they, showed him the instruments they'd used to cut out his entrails and remove them through his gonads and stuff like that. And he quickly recanted. That sort of thing. So it was not necessarily a wonderful time, but the main thing is, luckily for Galileo, a good friend of his who was a cardinal and in fact had given him the permission to write the book that he wrote that got him into so much trouble had since become the actual pope. So had it not been for that, the pope might have actually had him put to death, but instead they sentenced him to basically life at home, and they forbid him to study astronomy and to report on astronomy anymore. So what he did was he decided he would use the rest of his life to try to figure out motion, because one thing was obvious, and that was the fact that under all models that existed for the universe, i.e., the solar system, on all of those models, Jupiter was a moving body. And he had seen through his telescope, not that he invented the telescope, he had read about the invention of the telescope and made a telescope for himself, and in fact made it better. And what he really did do was one of the first. He was one of the first people to actually look at the heavens with his telescope. And when he did, he saw that Jupiter actually had these little companions, and he called them the Medicean moons. And those Medicean moons were Io, Europa, Ganymede, and Callisto. And he plotted them, and you could see that over time they always stayed there with Jupiter. So one of the major model or one of the major ideas coming from Aristotle was that if a bird were sitting up on a tree limb, for instance, and saw a worm down on the ground, if the Earth was actually orbiting around the sun, and then that bird saw that worm and decided to lift himself off the limb to go get the worm, then the planet would leave him behind. So that was their understanding of physics. And here was Jupiter showing that that wasn't the case. So Galileo went to in-house arrest and decided to study motion. Well, when you study motion, you might notice, for instance, that when you take a pin, I don't want to drop that one, but when you take a pin and you drop it, it's not obvious. Does it immediately jump to some speed and then travel at that speed all the way down, or does it slowly speed up, speed up, speed up, and continue to speed up till it hits the ground? Because Aristotle taught us that all things fall, but their rate of falling was directly proportional to their mass. So his idea was more along the lines of when you let go of this pin, it's going to immediately take off at some velocity corresponding to its mass. And if you took a pin that was twice as heavy and dropped it, it would fall twice as fast, right? So that was the idea. But if you try to look at it, you can see it right now. It's really hard. You can't tell whether that's speeding up or what. So what Galileo came up with was, hey, I'll study things going down an incline because I know the vertical component of the motion will always be proportional to the actual vertical acceleration that we have in free fall, and I can always get that back by using trigonometry. So he studied inclined planes and gradual inclined planes, and what he discovered was that when he allowed an object to roll down an incline, it sped up. When it rolled up an incline, it slowed down. So he argued that if the surface was in fact level, he'd expect it to go forever, which was in stark contrast to what Aristotle taught, because Aristotle was teaching that basically there's four elements: earth, wind, water, and fire. And those four elements dictated how things behave. So, for instance, if you considered an object like a rock is made of earth, and its natural place is the center of the earth. And therefore, if you pick it up, it will naturally race towards the center of the earth, and that's part of its natural motion. If, however, you tried to move that rock left or right, then that was violent motion, and the only way that could occur is by the sustaining of a force. In other words, you'd have to completely apply a force to it at every instant as long as you want it to keep it moving. So that was the idea how motion worked. But Galileo's saying, hey, it looks to me more reasonable to assume that motion, whatever motion it is, will stay the same uh, no matter what, because I've rolled these balls down inclines and they speed up, and I've rolled them up inclines and they slow down. So rolling on a horizontal surface would suggest that it's never going to speed up or slow down. And he went on further, and like he would imagine, or actually did experiments allowing a ball to roll down an incline and sort of like a half pipe, like you might see in the X Games or something like that. It would then roll up another incline. And what he realized was that the ball rolling down would come to about the same height on the other side. So then he looked at it closely and he realized, okay, well, it's doing some skipping and some sliding and, some stuff that looks like the motion is kind of hindered by maybe some extra forces. So he went and polished the surface really well and, sanded it down and got it really smooth. And lo and behold, then when he let the object slide down the incline from one side, it got even closer to reaching the same height on the other side. He polished it some more and it got closer still. So he reasoned that if he was able to actually get rid of whatever those extra pushes and pulls were, that it would always tend to go from the exact same height it started at to that exact same height again. if you imagine that second incline being very, 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 very gradual, then that object could go many, many, many miles before ever reaching the same height it initially had. So again, he was able to reach the conclusion that it seems objects on flat surface do not have any tendency to speed up or slow down. Their natural inclination is to maintain their motion. Specifically, like if it's moving at 3 meters per second due east, he expects it's always going to move at 3 meters per second due east unless some force tries to alter that motion. And just even though he was kind of brash and didn't really care about smacking Aristotle in the face, he sort of came up with the idea of inertia by basically, it's not an answer to the question, why does motion happen this way, but it's at least a way that makes you feel a little better about objecting to what Aristotle said. It's like, oh, well, Aristotle didn't know about inertia. So, what inertia and we'll actually see that's turns out to be just mass. But what inertia is a reluctance to accelerate, a reluctance to change an object's velocity. So, objects have some reluctance to change their velocity. And remember, velocity is a vector quantity. So, that means not speeding up, slowing down, or changing direction. So that was where we got Galileo's law of inertia. Is he basically said objects tend to maintain their state of motion, or if they're sitting still, they tend to stay in that sitting still state unless acted upon by some external force. So that was Galileo's law of inertia, and that in fact turned into the equivalent of Newton's first law of motion. So when Newton says that if I have seen further than others, only because I stood on the shoulders of giants, in this case he's talking about Galileo was right. Galileo gave me Newton's first law of motion as Galileo's law of inertia, and now we've called it Newton's first law of motion. Not only that, I was lucky enough to be in Utah, Salt Lake City, Utah, when a Leonardo da Vinci exhibit was going around, and they had it at the local museum there, and I got to go in. I've always been a big Leonardo da Vinci fan, and when I went there, I actually saw in a notebook it was laying out, and of course you had to translate it, but it said what the translation was. But basically, what Leonardo da Vinci had written was it's obvious that when a eagle pushes down on the wind with a force of 50 pounds, and I can't remember, I think it was pounds is what they called it, but either way, that the wind will push up on the eagle with a force of 50 pounds. That's Newton's third law of motion, and that's, Leonardo da Vinci talking about it. So Newton's third law of motion was also already studied, and people had already reached that conclusion well before Newton had. So, in some sense, Newton was being historically accurate to say that he had stood on the shoulders of giants. Okay, so now with that in mind, let me go ahead and share my iPad screen with you so you can see what I've written down for Newton's three laws of motion. And okay, so I've just taken the time to write them down. And this is in my own words. You can write them down in the words of the book. Whatever you want is fine. Uh, what's going to happen is if I ask you any questions about these laws that I told you should commit to memory, I'm going to be using the wording from the book. So imagine I'm not asking you to be able to state these verbatim from the book definitions, but it's not unreasonable for me to say memorize the book definitions and then think if I were to take out one important word and change it with another word, would you be able to detect that that is not exactly the Newton's first law of motion or Newton's second law of motion? So that's the kind of way I want you to think about it. Think about, could I tell the difference between Newton's actual first law of motion and a version of Newton's first law of motion that might not be true because I've changed a key word in it? So again, these ways that I've written it down are just ways for you to remember which ones are which, but you should probably commit to memory the actual text versions as well. So, in other words, don't memorize mine. They're just ideas to get you to remember which one's Newton's first law, which one's Newton's second law, and which one's Newton's third law. But then you'll go and memorize Newton's first law as written in the book, Newton's second law is written in the book, and Newton's third law is written in the book. So let me start off with Newton's first law. I wrote as N1. An object in motion tends to stay in that state of motion. That's a key thing there. I'm saying it's staying in that state of motion. Whatever state of motion means, I'm going to answer that in a second. But an object in motion tends to stay in that state of motion unless acted upon by a net external parenthesis non-zero force. Okay. Net. You guys are familiar with this because you probably had a job before, and net means your net pay. And for instance, they take your hourly rate, they multiply it by the number of hours. Maybe you get commission, they'll take your sales and multiply it by the commission percentage, and that'll be added up. But then they have to deduct FICA and Social Security insurance and all that good stuff. So the sum of all those additions and subtractions gives you your net pay. And that's what we mean here by net external force. I need to add up all the individual forces. Now, I've already hinted to you that force is a vector quantity, so that means you're going to have to use this newfound understanding of vectors and vector addition to calculate what the net force acting on a object or a system is. Right now, we're going to treat it as if the Newton's laws apply to a single body, but in principle, it could be, for instance, a box that has a string tied to it, and on the other end of that string is another box, and then that has a string tied to it, and the other end of that string is yet a third box. So you could treat the system that you're wanting to apply Newton's laws to as just the first box, and then the string would uh, be an external force. Or you could say the system is the first box and the second box, and the string between the first box and the second box would be an internal force and not one that Newton's law needs. But the string between the second box and the third box, that would be an external force on the system, and so on and so forth. Now, you could also say box one plus string plus box two plus string and then box three, all of those plus those strings is the system as well. And you can treat that there that way as well. So that's really the generality that you can do Newton's laws of motion. But we're going to start off simple as if we're just treating individual objects. So an object in motion tends to stay in that state of motion unless acted upon by a net external force. By net, we mean we're going to sum up all those forces. Sorry about that. And when I say external, I've hinted at that already. What I mean specifically is it can't be an internal force. Like if we treated the first box, the string between the first box and the second box as the object that we're applying Newton's laws to, then any force that the string applies to the second box or any force that the string applies to the first box, that's an internal force and it can't be part of Newton's laws. So you wouldn't count that. But that third box and that other string that's connected between the second box and the third string, that is an external force, so that can be connected. Now, if those forces add up and give you something other than zero, then the object will change its state of motion. What is the state of motion? I said state of motion. What is its speed and direction? That's really the state of motion. I want to know not only how fast it's going, but in what direction. And when I say an object tends to stay in that state of motion, that means that its speed is not going to change. It's not going to slow down or speed up. And its direction is not going to change. It's not going to change directions at all. So that's what Newton's first law says. It says if the net force, the net external force acting on a system is zero, then the object will not change its state of motion. If I wanted to say that in fewer words, I would say the velocity of an object is a constant unless acted upon by a net external force. Because remember, velocity is a vector quantity and it has a magnitude, which we often associate with the speed, and a direction. So by saying the velocity is a constant, I'm saying that it can't change its speed and it can't change its direction. So that's why that works. Any questions on that part? Okay. So that tells you something. For instance, I know that this Rubik's Cube has a certain weight associated with it. I know that the Earth has an affinity to pull this Rubik's Cube towards the center of the Earth, and therefore the force that the Earth pulls on this with is something we call its weight, and that is due to gravity. But if I had this Rubik's Cube sitting on top of a table, let's pretend this isn't my hand, let's pretend it's a table, then I know at least one force is acting on that Rubik's Cube. Specifically, the weight is acting on that Rubik's Cube. That's a force pointing downward. So, from Newton's first law alone, the fact that this Rubik's Cube is not changing its velocity tells you that that can't be the only force. There must be another force. And from that, we're able to reach the conclusion that the tabletop, not my hand, the tabletop that my hand represents, is applying a force to it that must exactly cancel out the weight. So the weight was pointing down and was equal in magnitude to the weight of the object. Well, there must be a force from the table pushing up on it, and that force must have the same magnitude but point in the opposite direction. So just by knowing Newton's first law of motion, we've now came up with a second force, and that force is what we call a normal force, or they sometimes call it a contact force or something like that. But sure enough, if you lay an object on a table, then as long as that table is strong enough to hold that object up, then that table is, even though it's an inanimate object, is applying a force to the object. And that force is what we're going to call the normal force. And we call it normal because it acts perpendicularly to the surface. If it acted at an angle other than 90 degrees from the surface, then that would cause the Rubik's Cube to move left or right or forward or backwards or something like that, in addition to canceling out the weight due to gravity. So that's why we reach the conclusion that it's a normal force. All right, so that's Newton's first law of motion. An object in motion tends to stay in that state of motion unless acted upon by a net external non-zero force. Newton's second law. Well, this is about what happens if the net external force is not zero, right? We know from Newton's first law or from Galileo's law of inertia that when there's no net external force acting on the system, it's just not going to accelerate. It's not going to change its velocity, right? But what happens when that force is not zero? This is the part that Newton came up with all on his own, and it's called Newton's second law. An object of mass m, and this could be a system of mass m as well, but I'm saying an object of mass m will experience an acceleration a vector that is directly proportional, parentheses, and parallel to the net external force, and inversely proportional to its mass. So this is that thumbs up, thumbs up, thumbs up, thumbs down verbiage that I've been using, and I want you guys to adopt from a conceptual standpoint. So if you look at the A on the left-hand side of that equation right here, that A doesn't appear to be in any fraction, but it definitely appears to be on the left-hand side of an equal symbol. And the net external force, which is what that sigma here means, that sigma that uh, looks like a E written kind of crooked, that means sum up all the forces. So it's a way to remind you that Newton's second law isn't about a particular force being equal to mass times acceleration. It's about the sum of all the external forces acting on the body of mass m. You have to add all of them up to get the net force. So that's what this right here is the net force. Since the net external force and the acceleration are on opposite sides of the equal sign and on the same side of the fraction bars. Again, there's no fraction for A, but that means you can write it over 1, and then you'd see, oh, A's in the numerator, just like the total force is in the numerator. And when you have two quantities on the same side of the fraction bar, but opposite sides of the equal sign, they're thumbs up, thumbs up. What that means, since there's no exponents on that, is if I double the net external force, if I took the net external force, which might have been 100 pounds northward, and I doubled that to make it 200 pounds northward, then the acceleration would go from whatever it was before to twice as big. If I increase that net external force by a factor of 1.78, then the acceleration would increase by a factor of 1.78. Notice I'm multiplying slash dividing. I'm not doing any adding or subtracting. Similarly, thumbs up means thumbs down, thumbs down. So if in fact I decrease the net force by a factor of 2.78, then the acceleration is going to decrease by a factor of 2.78 as well. So that's the first part of this. An object of mass m will experience an acceleration a that is directly proportional and parallel to the net external force and inversely proportional to its mass. So inversely proportional, notice the m is in the denominator. The m and the a are on opposite sides of the equal symbol, but they're also on opposite sides of the fraction bar, so that makes them thumbs up, thumbs down. Okay? Now, what that means is if the mass goes up by a factor of 8.49, then the acceleration is going to go down by a factor of 8.49. If m was squared, it'd be different, but m or m cubed, it would be different. But in this case, where there's no exponents, it just means if one goes up by a factor of some number, the other one's going to go down by the exact same factor. Now, you can also solve this for the net external force, in which case you get the net external force summation of forces F is equal to m times a, and that's a vector equation. And generally speaking, if you use x, y, z coordinates, that just means you could break this down into three separate equations. One equation being the summation of all the forces acting in the plus or minus x direction is equal to the mass times the acceleration in the x direction. The summation of forces in the y direction is equal to mass times acceleration in y direction, and the summation of forces in the z direction is equal to mass times acceleration in the z direction. Okay? So notice that the acceleration and the force, thumbs up, the acceleration and the mass, thumbs up, thumbs down. So what's going to turn out to happen is I've already talked to you about weight. Remember, I said the affinity that the Earth has for this Rubik's Cube is the force of gravitational attraction that the Earth has for the Rubik's Cube, and that quantity is called its weight. Well, you'll find out in a second because I'm going to tell you what the formula for weight is, but what you'll find out is that weight is directly proportional to mass. So if you double the weight of something, in other words, go from a pin that weighs 100 pounds to a pin that weighs 200 pounds, then you've increased the force by a factor of two, and therefore you've also increased the mass by a factor of two. So there's a mass term in the numerator that just doubled. Well, guess what? If the mass doubled, then the mass in the bottom also doubled, and that meant the 2m on the top and the 2m on the bottom are going to cancel each other out, so you get the exact same acceleration whether the mass is m or 2m, because the 2m on the top cancels with the 2m on the bottom, and if it's 1m, the 1m on the top cancels out with the 1m on the bottom. That's exactly why Galileo discovered that all objects fall at the same rate in free fall. Any questions on that? It's also why when they let old people like me play baseball, we don't play baseball, we play softball. And what we did to protect ourselves with that was we used a ball that's much, much heavier and less hard than a baseball. The fact that it's much, much heavier means that this mass is going to impede the acceleration so that when someone hits it, even though I'm now instead of 90 feet away, I'm only like 60 or 45 feet away, depending on where you're playing and what kind of sport you're playing. Now you have a less ability to achieve such a great acceleration, so I have more reaction time as the pitcher to actually catch it. So that's one thing. Another thing is it just also keeps people from getting hurt a little bit. But that's part of the deal here. That's also why I said the little girl would have a difficulty pushing the cart of 13 watermelons because the mass of the 13 watermelons is very large. And in order for her to make it accelerate, she'd have to put a really large force into it. All right, so that's Newton's Second law, what it's telling us is the acceleration is going to be parallel to the net external force. In other words, if you add up all the forces vectorially, like we learned in chapter 3, and the result is, 5 degrees east of north, then the acceleration is going to be 5 degrees east of north, period. Okay? It can't be anything different, even though m is multiplied by a, because m is a scalar and it can't be negative. So the only way a scalar multiplied by a vector gives you a different direction is if the scalar's negative, in which case it gives you the negative direction. In other words, it gives you the opposite direction. So since mass is a positive quantity, the acceleration is always going to be parallel to the net external force. You don't expect, for instance, if someone pushes you backwards to you to fall to the left. Or if someone pushes you to the right, you don't expect to fall backwards, right? You could because you could trip and stuff like that, but the main thing is that's not what the laws of physics tell us. Now, Newton's third law, and this is one of the laws that you could probably state for every action there is. Go for it.
Reaction.
Yeah, an equal but opposite reaction. That's normally what's said. And in fact, I teach like a conceptual physics class. And when I teach that, one of the books I used was like physics for art majors. And it said you can't touch without being touched. So it's a catchy little cheesy phrase like that. But that is in some ways the reality of Newton's third law. Newton's third law basically says if you apply a force to object A, as a result, in other words, if B, Billy, Mr. Younger, applies a force to object A, then that force will be FAB. So the first subscript represents the thing feeling the force, and the second subscript is the thing supplying the force. So the force on object A as a result of object B is equal to the negative of the force on object B as a result of object A. So the force that Billy applies to object A is FAB, and the force that A applies to Billy is FBA. And according to Newton's third law, they're equal in magnitude but opposite in direction, and that's because of that negative. Notice it also looks like the rule that I told you about when we did the addition of velocities. Remember, VAC is equal to VAB plus VBC, and I said, by the way, Fij is equal to the negative of Fji. Same thing there. It's that Newton's third law type of idea. Now, just to give you an idea of the conceptual grasp of this, if you've ever tried to kill a fly, flies get to be a pain. I'm not necessarily a person that chooses to kill insects, even insects, because they don't matter too much in the everyday scheme of things. But I personally don't kill live things unless I'm going to eat it or something like that. So I don't necessarily kill flies unless they're really aggravating me. But if you've ever tried to kill a fly by swatting it out of the air, you'll notice that what happens is if you're lucky enough to actually hit the sucker, he'll go off and he'll be sort of stunned, but he keeps flying around. And you might wonder, well, why is that? Surely, me, this 250-pound dude can kill a itty bitty fly. Well, Newton's third law is a quick and dirty way of saying the answer. Okay. I cannot apply a force to a fly that a fly cannot apply to me because Newton's third law says that whatever force I apply to that fly has to be equal in magnitude to the force that the fly applies to me. So if you think about it that way, if I wanted to actually put a 10,000-pound force on a fly, then that means the fly has to be able to apply a 10,000-pound force to me. And just the thought of it makes you think, even though you don't necessarily understand necessarily what a force is at this point, you certainly would be skeptical that a fly could give you a 10,000-pound force. If you want to think out the nuts and bolts of it a little better, imagine this. Imagine I would like to swat a fly and that I'm at the peak of my athletic fitness. Let's say I can, still throw a ball at very close to 100 miles per hour. So if that's the case, then my hand speed doing this could be as much as 100 miles per hour. Because obviously, if you're going to throw a ball at 100 miles per hour, if it's leaving your hand at 100 miles per hour, your hand must be moving at 100 miles per hour at that instant, right? So if I try to move my hand at 100 miles per hour and then hit a fly, what happens to that fly? Well, what happens is I hit that fly who was initially sitting still, and you might think that maybe over the width or the thickness of the fly will go from going 0 miles per hour to going 100 miles per hour. If you went ahead and calculated what that acceleration would be, you would say V finals 100 miles per hour, V initial 0, and you could say the change in X is maybe zero point 0.1 centimeter. So that's my delta X. And there you could take V final squared minus V zero squared and divide it by 2 delta X, and that would give me my acceleration. And you'd get a big acceleration. 100 miles per hour is what? That's like, I think that's like 29 meters per second or something, somewhere around there, around 29 or 20, 32 or something meters per second, somewhere in that ballpark. So we're talking, 30 meters per second squared over 2 times 0.001. So you get a pretty big number. 33 squared is pretty, or 30 squared is, 900. That's pretty darn big. And then you're dividing it by 2. That brings it down to 450. But then you're dividing it by 0.001. So you're bringing it back from 450 to what, 4,500? So maybe 4,500 or even 4,000 or even 45,000. Now, in Newton's second law, if this was 45,000, then yeah, that looks like that force would be really big. But guess what? The fly has a mass that's on the order of grams, and we're using the SI, and in the SI, we're supposed to use kilograms. So we're now talking the fly has a mass of something like zero point zero zero 0.002 or zero point zero zero 0.003, on the order of a few grams. So if you multiply zero point zero zero 0.002 by even 45,000, you all of a sudden get the 45,000s a lot smaller. So the net force has become quite small. It's still pretty big, but it's not, you aren't approaching 10,000 pounds or anything like that. That is the reason that you can't hit a fly hard enough to kill him because his mass is so low that it takes almost nothing for him to immediately accelerate from 0 miles per hour to 100 miles per hour. So if I really wanted to put a significant force in them, I would want to bring it up to an even larger speed or do it in even a smaller amount of time. In doing that, I would have to maybe make my arm go faster than I could even throw, even at the height of my best throwing, which wouldn't have been, even 100 miles per hour. But if I did that, then I could increase the speed a little bit, but the force is only going to go up by a little bit. So that's the deeper thought of how Newton's third law prevents us from, hitting a fly in the air hard enough to kill it. You could probably still do it if you hit it right and just the right way at just the right time. Maybe you have to hit it head on or something. I don't know. I don't really like thinking about killing little things or any things for that matter. But the main thing is because it's so light, it doesn't take much to accelerate, so we can't hit it very much. The same thing's true if you try to hit a piece of Kleenex. Like if someone drops a Kleenex and you try to punch it with all your might, it's going to take almost no force to bring that piece of Kleenex up to the same speed as your fist. So the force is going to be very small because the acceleration is very small and the mass is even smaller. Well, the acceleration might be big, but the mass is so small it's not going to matter. Anybody have any questions on that? Okay,
Yeah, so what if oh, sorry.
go ahead.
What if it was like something heavier like a car?
So yeah, and that's one of the demos I often do. So for instance, I'll take a big railroad spike, or we have this big hunk of steel that's about this big around, it's about that long, and I can take it and lay it in my hand, and then I take a mallet and I hit it with all my might right on top of my hand. I even make sure it's like laying on top of my knuckles so that it's, bone against hard surface, and I feel nothing. The reason why is, like you said, in this case, we're dealing with a huge mass. So when I hit it with a really high mass hammer, that high mass hammer is trying to accelerate that thing, but its mass is so huge, the acceleration has to be really, really small. And because the acceleration is really, really small, the acceleration times the mass gets a net force that's not very big, and I don't feel anything on my hand. That's also the same reason, like if you've seen people, and this is one of the demos I do in my class, is I'll put out a tablecloth and then I'll put dishes on top of the tablecloth, and then I quickly pull the tablecloth out from under all the dishes. That's Newton's law of inertia, Newton's first law of inertia, or Newton's first law of motion, saying that, hey, these objects would like to accelerate, but they can't unless a net external force is applied. I applied a force that was so large in yanking the tablecloth out that the inertia of the plates and stuff, they were not even affected by it. So instead of actually making the plates run off, the blanket just slipped out, or the tablecloth just slipped right out from under it. So, in some sense, you can look at that as heavy masses have a lot of inertia, and therefore they keep things from moving rather rapidly. And that's sort of what you were talking about when you were saying, what about hitting a huge mass? Does that make sense, Isaiah?
Yeah, that's perfect. So,
Okay. All right. So, another thing your book does, and it actually asks you this question. Let's first start off with example 4:1, a school bus comes to a sudden stop and all of the backpacks on the floor start to slide forward. What force causes them to do that? Anybody have an idea on that one? Be excited to offer a wrong answer, by the way. Never, ever, ever beat up yourself or feel bad about getting the wrong answer. All of the major discoveries, just about all of them, come from us making a hypothesis that turned out to be wrong. So it's really good to go ahead and do that. Anybody have an idea? I don't see anybody typing one. So there actually is no force. This is Newton's first law of motion. So what you have is a school bus, maybe going 40 miles per hour, blah, 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 like this. And then all of a sudden the school bus driver hits the brake. And then the book bags that are laying on the floor is usually kind of smooth and has some friction, like you can walk on it, but you're also liable to fall if you come in there with wet feet, right? Because it's so smooth. Well, the same thing happens with your book bags. There's not much friction between the floor and the book bags. So Newton's first law of motion says that these book bags are moving, 42 miles per hour, and then all of a sudden someone hit the brakes. The book bags continue to move at 42 miles per hour. The only way they wouldn't is if the floor can provide enough friction force to make it slow down. And it does, it makes it slow down so the book bags don't run up at, 42 miles per hour. And of course, the brakes didn't immediately bring it from 42 miles per hour to zero. But the main thing is it's the lack of a force to stop it that actually caused the book bags to slide to the front. Does that make sense?
Yeah, it does.
Okay. Now, after that, it talks about inertial reference frames, and basically the rule is this: if you're looking at a reference frame, and that could be just a coordinate system in space or whatever, you're just looking at something going on in the front seat of your car, or the driver's compartment of your car, or in your living room, or whatever. And you imagine a three-dimensional coordinate system or even a two-dimensional coordinate system, that is in some sense a reference frame. If you, while looking at that system, see an object just take off and start accelerating, yet you saw no force acting on it and you saw no ability of any force to act on it, then what you would have to conclude is that, oh dear, I'm not in an inertial reference frame because that object over there appeared to violate Newton's first law of motion or Galileo's law of inertia because it accelerated when there was no force acting on it, when the net force acting on it was apparently zero because I don't see any forces. So, in some circular way, that actually defines an inertial reference frame. Is if it obeys Newton's first law of motion, it's inertial. It's an inertial reference frame. If it doesn't, then it's not. If you take those merry-go-rounds that you see in playgrounds, the ones where you run beside it really, really hard, then you jump on and you spin real fast, or maybe you can catch some old Tosh.0 episodes where he, took a motorcycle or a moped or something like that and leaned it over sideways and had it speed that thing up really, really fast, and then people go flying off like Sim City and stuff. That's kind of fun to watch, as long as you don't know the people and you don't think anybody's going to get hurt, but people can get really, really badly hurt. Uh, in that scenario, imagine that merry-go-round type thing. Imagine if we mounted a video camera to it where it was close enough that I could see the surface of the merry-go-round, but I couldn't see beyond the edges of the merry-go-round, so I couldn't tell if it's moving or not. And it's bolted to the actual merry-go-round, so even if the merry-go-round's turning, the camera's turning too, right? In that scenario, if I'm looking at, let's say, a basketball that's sitting in the center of the merry-go-round and the basketball just sits there, then I say I'm in an inertial reference frame. I can't tell really whether the thing's moving or not because the view of my camera just shows the metal that I'm attached to. But if all of a sudden I see the ball take off and accelerate out of the frame, then I'd know it's a non-inertial reference frame. And what's happened there is someone has actually spun the merry-go-round, and because the ball was not dead center, it actually needed some kind of force to keep it in the center to make it follow a path that's technically a circle. And without that force, it therefore just shoots off in whatever direction it's already going, which is tangential to its motion at each point. So that's another example of a inertial reference frame and a way to see how it's non-inertial if the basketball, for instance, takes off. Anybody have any questions on that? All right, I'm going to go to mass now just to discuss this. So, mass, your book says a measure of the inertia of an object. It also calls it a quantity of matter. I've never liked any of those definitions, to be honest with you. What I try to do, and it's not necessarily any better, it just felt better to me, so I used it. But what I try to do is I think along the lines of all matter seems to be made up of atoms and molecules. Okay, obviously there's actually parts of atoms and molecules that aren't made up of atoms and molecules, but we're dealing with classical physics where we don't get so small as to discuss about atoms or whatever. But if you think about it that way, then you say, okay, well, each atom has a specific mass that's its inertia, its reluctance to accelerate. And you can measure that by trying to push it forward a little bit and seeing how much it resists. Find out how big of a force it takes total to apply to this little atom before it reaches a certain acceleration A. And then you can use that A and that force to calculate M, and that would be representative of the mass of the atom or the molecule. And you do that a bunch of different times until finally you got a good solid value for what the mass of that atom is. All right. Well, if all those atoms are identical, then you just multiply the mass of that one atom times the number of those atoms, and that would give you the mass of the object. That's the way I like to think about matter and mass. It's the sum of the masses of the individual atoms or molecules that make it up. Okay. That's entirely different from weight. So I want to stress that as well. Weight is an affinity that a body has for another body. So the weight is a gravitational force, and specifically on Earth, the weight is the gravitational attraction between the center of the Earth and the object that you're studying. Now, in our system, mass has units in the SI of kilograms. In the CGS system, this is the SI, but in the CGS system, it has units of mass equal to the gram. That's why it's called CGS, centimeters, grams, second, and that's why SI is called MKS because it's meters, kilograms, seconds, right? So the mass is measured in kilograms or grams. If you want to go to the British system, which again, it's only us and Myanmar or somebody that's using this, then the unit of mass is the slug. which again tells you immediately why we're not using the unit of mass within the British system. Now, if you talk about weight, now the weight has units of newtons. And in the CGS system, it has units of dyne. So you've probably heard of the phrase dynamometer, maybe, or maybe you've seen various bikes with the word DYN on it or something like that. Those are dynes, okay? And really, to be honest with you, 1 Newton is equal to 10 to the fifth dynes. That's because remember, a Newton is made up of a kilogram and a meter and a second, whereas the dyne is made up of a centimeter, which is 100 times smaller, and a gram, which is 1,000 times smaller. Therefore, 100 times 1,000 is 100,000, and you get 10 to the fifth. So that's why that is. Now, in the British system, the unit of force is the pound. And you can write it as the hashtag, or you can write it as the LB, or you can just write it as POUNDS. Okay. Now, I'm going to go ahead and give you guys, it's a little early, but I'm going to give you an argument for exactly how we calculate the mass, or excuse me, the weight of an object. We learned in chapter 3 and also in chapter 2 about free fall. An object in free fall has what forces acting on it? Can anybody tell me that? What forces are acting on an object in free fall?
Would it be air resistance?
It would be without air resistance because it's in free fall. We
Okay.
ignore the air resistance, but you're thinking along the right lines. It's just the way I worded
Gravity?
it was probably the worst possible way I could.
Oh, no. Is it gravity?
Yes, exactly. The only force acting on a body in free fall is the force of gravity. Okay. Now, we've called that force of gravity the weight. I've just get told you that that's the fact. That's what we call it. So, in free fall, the only force is gravity, which is called W for weight. So, if I take Newton's second law, let's just imagine one dimension here. So I'll say the summation of forces in the y direction is equal to mass times acceleration in the y direction. Now, I said the only force acting on a body in free fall is the weight. So that means the left hand side just becomes W, right? Now, the right hand side has to have the mass M, but we know Newton's second law says that mass m will be multiplied by the acceleration. Does anyone know what the acceleration of a free falling object is or what the symbol we use for that is?
Is it G?
G. And in fact, just like that, we now have the formula for the weight of an object. Weight is equal to mass times gravitational acceleration. Now, the gravity on Earth is 9.80. If you wanted to calculate the weight of an object on the moon, you'd have to take the acceleration of gravity on the moon, which is about 1/6 of gravity. So you'd take 9.8 and divide it by 6, and that would give you the gravitational acceleration on the moon. If you wanted to talk about, even though there's not strictly speaking a solid surface of Jupiter, if you talked about roughly where the quote unquote surface of Jupiter would be, the acceleration due to gravity there is about 29 meters per second every second. So it's literally almost 3 times gravitational acceleration. Therefore, if you took yourself and moved it to the equivalent of sea level on Jupiter, you would triple your weight. So in my case, I'd go from 250 to 750 pounds. So notice how the weight changes from one body to the other, but the mass is in some sense a property of the object and doesn't change. So what is this unit of force? Well, according to this, the weight is equal to the unit of mass times the unit of gravitational acceleration. Well, the unit of mass is the kilogram, and the unit of acceleration is meter per second per second. So, what we know is that 1 Newton is equal to 1 kilogram meter per second squared. So, that's another important fact that we want to keep. And that's going to come in handy. In fact, if you already had chemistry, you've been using that fact for a long time. Even if your chemistry instructor didn't tell you what was going on, he just told you, yeah, the units work out. Don't worry about it or something. They might have actually told you. I'm not sure. But that's how a Newton breaks down. Similarly, one dyne, one dyne is equal to 1 gram centimeter per second squared. So that's what a dyne is. And of course, you could also say that 1 pound is equal to 1 slug feet per second squared. Now, your book actually gives you some data on this so you'll know, but specifically, 1 pound is equal to 4.4, well, I'll say approximately equal to 4.45 newtons. So if you took a quarter pounder frozen and then you cooked it, it would actually lose some weight because some of the fat has turned to a liquid and then leaked out of the meat, if you will. And then you have a burger that's no longer 0.25 pounds. It's a little bit smaller than 0.25 pounds. Well, that's basically a Newton. So a Newton is a little smaller than a quarter pound. We have that. We have, and I also have 1 dyne or 1 Newton is 10 to the fifth dynes. So that's helpful as well. And I should say that G is equal to 9.80 meters per second every second. But that's also 980 centimeters per second per second. And that's also about equal to 32 feet per second per second. So those are all quantities that we might wish to know as well. Anybody have any questions on all that stuff? Okay, let's see what time it is. Let's see if I can pull this down here a little bit. Okay. We actually don't have a huge amount of time left, but we do have some time. All right, so I've now talked about Newton's laws of motion. Let's go ahead and work out some other stuff. Your book has these examples. Oh, yeah, 1 slug is about 14.6 pounds. Or excuse me, 14.6 kilograms, not pounds. So that's another value that might come in handy. I don't really require you to commit these to memory. I do expect you to know that a Newton is a kilogram meter per second squared because you're going to use that so often. But I don't need you to commit these to memory. But you do need to have some sense of how big is a Newton, how big is a pound, how big is a dyne, that sort of thing. So that's why I'm giving you this. All right, so let's look at example 4.2. Oops. So example 4.2 says, force to accelerate a fast car. Estimate the net force needed to accelerate a 1,000 kilogram car at 1/2 G. So A, the net force is equal to question mark. And what we know is the mass is equal to 1,000 kilograms, and the acceleration is 1/2 g. Now that means 1/2 of 9.8 is what we're talking about. And then part B, they want to find the total force necessary to cause a mass of 200 grams, which is a apple, with an acceleration of 1/2 g. So that's the problem we want to work out here. I want to start off with A, and the summation forces is equal to mass times acceleration. I'm just going to calculate the total force. In other words, we're acting like it's the only force, so the total force is the force. And in this case, we're going to say 1,000 kilograms times 1/2 times 9.80 meters per second every second. And what you're going to see is that is very close. It actually turns out to be 4,900, but we're going to say it's essentially 5,000 newtons. Cost 1,000 times a half gives me 500, and then times 9.8 gets me really close to 5,000 again. So that's the answer to part A. Now the answer to part B is the summation forces is equal to mass times acceleration. In this case, we got to convert this to kilograms, and we still have a 1/2, and we still have 9.80 meters per second per second. Now, 9.8 is really close to 10, so when I multiply it by 1/2, I get something really close to 5. But zero point 0.2 is really close to 1 over 5. So what we find out is that this is approximately 1 Newton. So 1 Newton is the approximate force necessary to accelerate a 200-gram apple to an acceleration of 1/2 g. Anybody have any questions on that? I'm going to do quickly example 4.3. And this one says, what average net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour in a distance of delta x equals 55 meters? So they're asking for the summation, the total force right there is what they're asking for. So I'm going to say solution. What I know is the net force has got to equal the mass times acceleration. And what I also know is that in this case, V final is equal to 0. And I can use V squared is equal to V0 squared plus 2A delta x to calculate my acceleration. So A is going to be V squared minus V0 squared over 2 delta x. That's going to be 0 squared minus. Now, 100 kilometers per hour, if you divide that by 3.6, you're going to get 27.8. So I square that, and then I divide this by 2 times 55 meters. And you notice that that does give us the units we expect, meters per second per second. So 27.8 squared gives me 772.84. Now I'm going to divide that by parenthesis 2 times 55 close parenthesis, and that gives me 7 point, it's actually a negative, 7.03 meters per second per second. So that's my acceleration, and it's negative. Now the summation forces is equal to mass times acceleration gives me 1,500 kilograms times 7.03. I'm really only concerned about the magnitude, and I only had 2 sig figs, so that 3 is not a sig fig. When I multiply 7.03 times 1,500, I get about 11 times 10 to the third newtons. It actually equals 538 newtons, but there's really only two sig figs, so that's what it came out to be. Anybody have any questions with that? Now, the reason why it's negative is because you have to apply the force in a direction opposite the direction it's going. And that seems reasonable, right? If you're going 50 miles per hour and you want to slow down, someone better push you from in front in the opposite direction. And that's why it came out negative. Uh, I will finish off the rest of the examples for chapter 4 in our next meeting, but you folks are free to go. Don't forget to chat me your first and last name if you haven't done so already. And have a wonderful evening. And thanks for coming. I'll wait for the last person to leave in case anybody has any questions.
Thank you. Have a great night.
Thank you, Jonna.
Professor, I had a quick question.
Yes.
About last week's lab. Am I still able to turn it in, even though it's going to be late?
Hold on a second, Isaiah. I'm barely hearing you, and I couldn't make out what you said. Sorry about that, buddy.
Oh, sorry. About last week's lab.
Uh huh.
Am I able to still turn it in, even though it's late?
Yes, I leave all my lab turn-in areas. I don't have a final date on them because sometimes I get a little bit behind on my grading of lab reports. So my general rule is when I start grading the lab report, if it's there, I'm not going to count you as deserving points taken off. I generally don't do that to students. So as long as you get it in pretty quickly after the due date, you're probably not even going to lose points.
Awesome. Thank you so much.
You're welcome. Good luck, bud. Anybody else? Now, I should post this video online tonight. If not, it'll be up first thing in the morning. And I do post these notes immediately every night. So they're in my Google Docs, usually within 20 minutes after class is over. Isaiah, Aiden, Kyle, do y'all have any more questions? All right. Well, it looks like everybody has chatted me their first and last name. Yes, everybody's done that. So, well, thank you for coming, everybody. Have a good day. Bye bye. Last second to chat me if you still have a question.